The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. This is Kevin Humanik. Thank you for attending today's SLCan webinar. Today we have Frederic Genest from SLCan to deliver his presentation, Adapting to Climate Change, Weather Data for Building Design and Energy Calculations. Frederic's here to present this topic, and I'll introduce him by way of his biography. Frederic has worked since 2017 for Natural Resources Canada and at the CanMet Energy Research Centre in Varennes as a research engineer in the Buildings Group. He's assigned to the Greening Government Operation Program, and most of his tasks revolve around supporting federal departments in meeting greenhouse gas reduction targets, which are set by the Government of Canada. Previously, Frederic worked for 19 years as a building design consultant in mechanical engineering, where he developed a notable expertise in HVAC systems and controls, building energy modeling, and sustainable design. So thank you, Frederic, for attending and presenting today.
Thank you, Kevin.
Without further
yeah, I'll start then. Sorry. Okay, thanks. Let's thank the audience for being here today, and I wish to extend my best wishes for the new year to everyone. Before I start, I need to mention that I'm not an expert on climate change. I'm a building HVAC designer by trade. This presentation comes from my own preoccupations regarding building design and climate change, and stem from my best interpretation of the information available out there. So you need to take what I say with some grain of salt. This presentation is not an expert view on climate change issues. It is not an official or unofficial point of view of Natural Resources Canada on the question. Everything here is presented as is, and any use of that information for the audience purpose is everyone's sole responsibility. I don't want to scare anyone, but as engineers and architects and designers, we need to assume responsibility of our designs, and the presentation that I'm making here is to help you make better informed decisions. Oh, well, my screen is frozen. Sorry, one moment. Okay, good. So the objective of the presentation are as follows. First, I want to do a quick survey, a review of the weather data used in building design and all the related calculations. Then, before moving to impact adaptation and vulnerability studies, which contain information that can be useful for designs, I want to present an overview of the climate change modeling framework so that we can better understand the vocabulary that we found in the IAV studies. Afterwards, I'll move back to design weather data for buildings and discuss what we can do regarding the future climate. And I'll finish this presentation discussing more specifically on the weather files that are used for energy modeling. So moving on. Building designs and calculation procedures generally require knowledge of the local weather patterns in order to correctly size the HVAC systems and other building components. Temperature is used to calculate cooling and heating loads, for example, or to evaluate an air source heat pump capacity or performance over the year. Solar gains are used to, again, for cooling load calculation, but also for passive solar heating or PV production, for example. The rain patterns influence the rain screen design, the water retention, harvesting, and the snow load on roof, and etc. So knowing what is the current weather is good, but with climate change, we are moving forward with different weather patterns, and we need to prepare for them. Information on weather is currently found in many sources. One of the most used is Appendix C of the National Building Code. Here we see an excerpt from that table. In that table, we can find information regarding design temperature. For example, the 15-minute rainfall typical for the site, snow loads that are used for calculate the bearing capacity of roofs. This design is peak load, is based on the recurrent extremes for the location. The problem that we see with climate change is that those recurrent extremes are based on the climate normal for the site, so on the past climate. So far, past climate was changing rather slowly, and that information remained adequate for, I don't know, the last 100 years maybe. But with the upcoming climate change and those changes are becoming faster and faster, we can expect that those design values may not be as good as they were before. And we may end up in system components of the building that are under-designed or unable to achieve the service for which they were designed initially. Other common references for weather data are found on various websites, including this website here, climateweather.gc.ca, which is hosted by Environment Canada. There we can find historical weather and climate normals, but also the engineering climate data sets, which include design information for rainfall, the Canadian Weather, Energy and Engineering data sets, which are recorded observation for about 30 years. And the Canadian Weather Year for Energy Calculations files, the CWEC files, which are used for energy modeling. The currently available information is limited to the information you see on this slide, but data files going further back in time are also available if you ask for them at Environment Canada. Before I go further, I want to do a slight comment here. This presentation will include slides with references like this one. For some of those slides, I'm going to move quickly through them, just long enough, pausing long enough for the recording to occur, and so that you can consult the information at a later date. Aside from that, I'll be moving normally through the slides of this presentation. Other references for the data are a new website from ASHRAE, where you can see all sort of links toward information published by ASHRAE. There are also two other websites where you can get historical data for Canadian locations, among other things, and also international ones. One of them is commercial in nature, and the other one is public in nature. These historical data are often available in the file type that is suitable for energy modeling, either directly usable by Energy Plus or CanQuest. History is great, as I mentioned before, but with global change, global warming and climate change, the climate normals may not be still available or appropriate. Will your site be subjected to a local warming or a local cooling? Because that can be the case in some locations. How much are the new recurrent extremes predicted by climate change going to be even more extreme than those of today? Will we see new weather conditions that we need to prepare against? For example, frequent tornadoes or prolonged drought that we need to account for in rainwater harvesting systems. So if a building component or system is designed today, how will it perform in 20 or 30 years? If it doesn't perform well, what will be the cost of retrofits? Are you ready to handle that, or do you want to prepare against it? So, these are questions that are important, but unfortunately, they are not easy to answer. So moving on to the climate change framework, presenting the vocabulary that is found in the impact, adaptation, and vulnerability studies. All the climate change framework is led by the IPCC, which is for which the purpose is to organize and assess the scientific body of knowledge available and published regularly. The objective of the IPCC is to trim through the data, retaining only what is agreed upon or widely known or widely accepted, and not discuss too much or not give too much importance to information that is sketchy in nature or uncertain. So all its works present level of confidence on the information presented therein, based on the type, amount, quality, and consistency of the evidence in the literature. It discusses also the likelihood of a change occurring based on the statistical analysis or model results using expert judgment. So the vocabulary used in the IPCC reports are use words like highly probable or not likely, or we are very certain that this will occur or that will not occur. The IPCC is also responsible for many publications, including the regularly published assessment reports starting back to 1990, with the first assessment report, the second one in 96, the third in 2001, the fourth in 2007, the sixth 6 years ago. The next assessment report is planned for 21-22. The IPCC is also responsible for the methodological guidelines used to address or to prepare the GHG inventories by each country that is used to model the climate change. There are also some special reports and technical papers, including one that is very important that's titled Global Warming of 1.5 degrees C. That report highlighted the enhanced risk associated with not meeting the 2 degrees C temperature increase target that was set by the Paris Agreement. The report highlights the fact that if we are not able to maintain the global warming to a limit of 1.5 degrees C above pre-industrial levels, then we will suffer from a significant climate change impacts across the world. Climate change modeling is not an easy task. It uses global climate models similar to weather forecast models, which have generally a large grid resolution in order to span the entire globe. Over time, those weather forecast models have been completed with additional models to account for the various carbon cycles, the effects of ice sheets, the presence of dust and aerosol in the atmospheres, and other parameters influencing global warming, the greenhouse effect, and climate change as a whole. So in the end, we now today have a group or a series of models that is called the Coupled Model Intercomparison Project. These models are previously agreed upon by the experts of the IPCC and are used across the world to model climate change. Each model has its own set of strengths and weaknesses, which produce, in the end, a range of possible changes due to a given world emission scenario, for example. So that gives us a confidence interval for temperature changes according to a high emission scenario or a low emission scenario, for example. So that's why you will see in the studies a 20th percentile or a 50th percentile or the 75th percentile of values for temperature change, for example. Up until the assessment report 4, the process to get information on climate change was very linear. So, initially, we start with emission and socioeconomic scenarios, the IAMs, which describe what's going on in the world, how the population evolves, and how the economies evolve, and what is the use of energy, and thus what is the emission scenarios associated with each of them. Those emission scenarios are translated into radiative forcing, which is a way to account for the additional heat gains the planetary system suffers due to climate change, due to the rise in the CO2 concentration in the atmosphere. That radiative forcing is then transferred to climate models to get climate projections of what will happen in the future. Those models are always calibrated with past emissions that are recorded and with past weather to ensure that they are adequate, and then they are run forward in time to get those projections. Once we get the projections, Then we can combine them with the socioeconomic scenarios and evaluate impacts due to climate change, what can be done to adapt to them, and what are the vulnerabilities of the socioeconomic and natural systems. Up until AR4, the economic scenarios were grouped into 4 main families. The A family of scenarios was more focused on economic growth and with the world essentially disregarding the climate change threat. The B scenarios were more ecologically friendly and where the world was more more conscious about the environmental impact of the human society and indirectly tackling the climate change threat, a little bit like we see today with all our discussion about sustainable design and sustainability. Horizontally, the 1 family shows a world where the growth and efforts are global in nature, which means that these scenarios have more impact on the environment. The 2 family, the next row, show scenarios where efforts are fragmented and less organized and which have a less impact on the world as a whole. Starting with AR5, the process is a little bit different. The process is parallel in nature to speed up the process and get to results faster and use the results from a previous iteration into a new iteration much faster as well. So we start with RCPs, representative concentration pathways, which are based on what the literature has reported regarding emissions. And RCPs are set based on to obtain a range of emission scenarios and clearly distinguishable climate futures. On the right, you see the 4 main RCP retained for the studies. RCP 8.5, which is deemed business as usual sometimes, and which has a high emission scenario, down to RCP 2.6, which is a scenario more aligned with the goal of maintaining global warming below 2 degrees C compared to the pre-industrial levels. The RCP forcings are then used in the climate models to get the projections. At the same time, emission and socioeconomic scenarios are developed to match the RCPs and can then be used jointly with the projections to get impact adaptation and vulnerability analysis done. This graph presents in more detail the 4 main RCP used for modeling. So the number associated with the RCP 8.5 or 6 is linked to the radiative forcing used in climate modeling, which is in watts per square meter. The graph on the left indicates the corresponding net emissions and expected concentration, CO2 concentration levels we can get with each RCP. On the right, we see the 4 main RCPs with the expected increase in temperature related to pre-industrial levels. The bunch of lines, as you see there, are basically 1,000 emission scenarios that have been considered in order to set the 4 main RCPs shown here. RCP 4.5 shows a world that is active toward mitigation and reduction of greenhouse gas emissions, but not enough to reach the 2 degrees C target. RCP 6 shows slower growth, economic growth, I mean, and some durable mitigations, but this is not an RCP scenario that is often used in the various studies. Okay. Again, presenting the RCP, but the graph shows the expected global average temperature change relative to 2000 this time instead of pre-industrial level. As can be seen from this graph, the current trajectory in emissions follows the historical trend and tends to be aligned with the RCP 8.5 scenario, unfortunately for us. New for the next assessment report, we're going to see 3 additional RCPs added to the group. RCP 7, which is a new baseline RCP emission scenario, which is considered to be more aligned with the current GHG emission trajectory. RCP 3.4, which is going to be a what-if scenario used to represent the world attempting to meet the 2°C target, but failing to do so. So a little bit aside the target, and which will lead to a rise in global temperature in the 2 to 3°C instead of below 2°C. The RCP 1.9 is a new scenario that is designed to show the impact of attempting to meet the 1.5°C target. For the next assessment report, we also will discuss new shared socioeconomic pathways, which are baseline socioeconomic narratives or storyline describing the world as it is and as it could be if without explicit consideration for climate change. So we have 5 economic scenarios. Our SSP1 and SSP5 are narratives that are rather optimistic regarding economic growth and social development. However, SSP1 assumes a more sustainable path, focusing less on material and energy use and with the general use of renewable energy rather than fossil fuel. SSP5, on the other hand, is fossil fuel inclined. Basically, rapid development of technology and faith in that technology to manage the environmental impacts. SSP2 is somewhat of a middle-of-the-road scenario that assumes a continuation of the current world trends. SSP3 and 4 are pessimistic in nature. They assume that the world will that the world inequalities will keep rising, that we'll see a regional rivalry between countries and within countries due to resurgent nationalism and global competition, something that we can all agree that is making currently the headlines. Energy and food security goals are going to be important. So SSP 3 and 4 are rather material intensive, but they are different in the nature of the conflicts that we see in the world. The SFPs are used to estimate which emission pathways, the RCPs, are most probable in each scenario, and thus what are the most reasonable climate change scenarios applicable to each of them. As we'll see, in some SSPs, we see that some RCPs are excluded from occurring, either because they are deemed unachievable or highly improbable. So from this graph, SSP5 and SSP3 predict significant GHG emissions that are represented by RCP7 and 8.5, leading to important global warming impacts. The lower RCP scenarios remain possible, but they are not deemed very likely with those SSPs. This is why those scenarios are deemed highly challenging when considering climate change mitigation. Bottom left, the SSP1 is located there because it's deemed to facilitate adaptation or have low mitigation challenges. This scenario managed to easily avoid the high emission RCPs and putting within range the most favorable ones, the RCP 1.9 and 2.6. SSP2 and 4 tend to be middle range in emission scenarios, with RCP ranging from 3.4 to 6. with SSP4 managing to avoid the high emission scenarios due to the socioeconomic fragmentation of the world. In this scenario, SSP4, the fragmentation of the world means that the poorer parts of the world are becoming poorer and are thus less economically active, having less emissions, while the richer parts can more easily afford clean energy source and mitigation. Within a coherent world, represented by SSP1 and 5, adaptation is rather easy, while adaptation is considered difficult in the fragmented scenarios. Now, with this vocabulary in place, we'll move in the section of the presentation about impact, adaptation, and vulnerability studies. The purpose of these studies is to assess the impact of climate change on socioeconomic and natural systems. They identify the negative and positive consequences of climate change by considering the vulnerabilities of these systems as well as their capacities and limitations to adaptation. When possible, options and suggestions for adaptations are present. The studies can be very global in nature, broadly discussing the climate change impact worldwide or of a country, or have a very narrow subject matter, focusing, for instance, on maritime transportation. The information found within is generally quantitative in nature, though some can present expected socioeconomic costs for mitigation or adaptation, depending on the organization behind the preparation of that report. We need to be careful when reading AEV studies because it is difficult or challenging to interpret information obtained from global circulation models at a regional level. Sorry. As you can see on the far left, global circulation models are used for worldwide modeling with grid resolution in the hundreds of kilometers wide. A single square of the model can represent a large region. For example, the red square on the left over here is bigger than southwestern Ontario. An area that big represented as a single data point means that many local weather patterns are completely ignored by the model, as shown by the sin wave over here. Having 1 point, only 3 points represent the sin wave means that we see that sin wave as a line instead of as a sin wave. To properly model such a region, we need a much finer grid resolution with 10-kilometer wide areas. In that way, we can get a better representation of sin data, for example. The necessity of such resolution is illustrated by the graph at the right, where the global circulation models properly represent rainfall, daily rainfall over the Alps. But as you get to more intense rainfall, the GCMs fail to properly represent or even notice those rainfalls, while the regional circulation model has a good result overall. As an example for an IAV study, we'll present the recent Canada Changing Climate Report published in 2019. The study was prepared by Environment Canada along with Natural Resources Canada. It presents the more direct impact of climate change on the weather patterns. This study is meant to be a starting point for more detailed and specific studies we publish at a later date. This is a summary of the findings reported in that study. Basically, what we have observed so far in annual mean temperature change is an increase of 1.7 degrees C since 1950, which is twice the world average observed so far. In the north, the increase is even bigger, up to 2.3 degrees C. By the end of the century, we expect an additional increase of 2 degrees C up to 6 degrees C, depending on the emission scenario considered, with more hot extreme and less cold extremes during the year. Precipitation is not expected to change much over the year. However, with shorter winters, we expect to see less snow during that period. So that's a bad news for all the skiers out there. Shorter winters mean earlier spring thaws and longer growing seasons. But that also means that nuisable plants and animals are susceptible to migrate from the south up to our regions. And that's why we see an increase in occurrence of the Lyme disease, for example. Climate change should also increase the frequency of weather-related events such as forest fires, rainfall, floods, heat waves, and tornadoes. Besides the qualitative information, some quantitative information can be found in the report. For example, the predicted change in temperature is shown in the table on the left. It can be seen that the information covers large geographic areas like the prairies, Ontario, Quebec, or the Atlantic. The information is presented for two RCP scenarios, 2.6 and 8.5, for two different time frames, and with three distribution percentile. So in order to design a building, which information will you use based on this table? It's not easy to find the right one, if the right one is even available. The graph to the right illustrates another information, which is the change in occurrence for extreme temperature events. Based on this graph, we can generally see that an extreme temperature occurring once per 50 years in the normal climate is expected to occur 3 times more by mid-century. This increase in occurrence is the same for a 20-year event or even a 10-year event, which is expected to occur every 4 years or about. If we consider the worst emission scenarios, RCP 8.5, the change is even more drastic. Events occurring once per 50 years is expected to occur 10 times more often by mid-century. And by the end of the century, should be an almost yearly event. So based on this information, a designer could tentatively pick a temperature extreme occurring at a 10-year frequency for its location and assume that it could be the new design normals. But how reliable is this approach? Another example of AAV study is the climate hazard assessment for the National Capital Region, completed recently for Public Services and Procurement Canada. The objective of this initiative is to have a better understanding of the changes to the climate for the Ottawa region, and thus evaluate the potential impacts for the Crown-owned buildings of the Capital Region. Once those impacts are evaluated, PSPC will be able to decide which measures are needed to mitigate and or adapt the building to the new threats, especially for the more critical ones. This report is expected to be made public in the near future. PSPC is looking for the right location to deposit this report. PSPC also intends to reproduce the same study elsewhere across Canada to have the same discussion with the Crown-owned building over there, but also to serve the public sector, or the private sector, I mean, sorry. Some of the findings of this report are shown here. We're showing the table the variation in with the normals for the RCP scenario 8.5 for 2050. What we can observe here is that the annual mean temperature should be about 3 degrees C higher, and we should see about 15% less annual heating degree days in Ottawa by 2050. The changes during the cooling season are more drastic. More heat waves with at least 5 times more days above 35 degrees C, which is a typical threshold considered because that's at this point that the heat waves start to take a death toll that is significant. We also expect to see about twice more cooling degree days during the summer by 2050. Annual precipitation should remain about the same, but the 1-hour rain event should occur once per 12 years instead of once per 50 years. Basically, that kind of information says that instead of having downpours across a few days, we may see a rainstorm event only, where all the rain is falling at the same time, and then no rain for a few days. This will have impact on all the water flow at the surface of the ground, what retention is needed, and etc. Other extreme weather events, such as tornadoes, are not expected to change much by 2050. There are other adaptation works underway in Canada. The National Resource Council has an initiative related to the climate resilient buildings and the core public infrastructure. This initiative aims at publishing new information in the Model National Building Codes, adding climate change design information in various publications, standards, and guidelines in order to serve the private sector more efficiently. The Standards Council of Canada is also responsible for many projects related to climate change. Their interim report published recently lists all the work completed so far. One work of interest is a guidance document on the use of weather data, climate information, and climate change predictions by building designers. So I suggest to those interested in that topic to consult the report and search on the web, on their website, the appropriate reports. I have found it, so it's available currently. These slides, the next 3 slides will present a list of websites with additional IAV publications. Each organization publishing those studies try to answer different questions. For example, the Institute for Catastrophic Loss Reductions publish studies focusing on the economic impact of climate change from the perspective of insurance companies. So, and that influenced the decision made by those companies regarding your insurance. Some of the EAV efforts in Canada are distributed geographically, where provinces are grouping together their efforts to have more resources made available for this task. Some cities are also investing in their own specific studies, and the list goes on and on and on. As could be seen, the current IAV information is generally not directly useful for building designers. Some of it can be adapted, but how confident would you be afterwards that the adaptation you made is appropriate? How to be sure that we're doing right? So some of the adaptation projects underway aim at answering the needs of the building community. So the joint NRC Environment Canada project is aims at adding new climatic information in the national building codes with the purpose of better accounting for the expected climate change. This work should be completed in time for the 2025 publication of the national building codes. With this project, they try to answer the question of how to account for climate change. So we can expect information for various emission scenarios and various level of risks. Similarly, weather files for building energy modeling representing various climate change scenarios should be made available within the next 2 years. But in the meantime, what can we do when we design buildings? Luckily, some information is available out there if you ask the right question and look at the right location. For example, this slide is extracted from a webinar hosted by the Ontario Centre for Climate Impact and Adaptation Resources. The presenter listed a series of climate-related data for Ontario, some of them directly usable by the building industry. Notably, in this slide, we can find the 1% and 99% daily temperatures, which represent the January and July peak design temperature used for sizing of the cooling and heating systems. We can also find intensity, duration, and frequency curve at selected location that can be used for the design of civil engineering works and rainwater systems. One approach to obtain relevant design data, sometimes hinted at in the literature, is the analog climate location approach. The idea of this approach is to identify key climatic parameters for the location of interest, obtain the expected change for a given emission scenarios called climatic anomalies, and select an alternate but suitably similar location for which the current climate normal corresponds to the future climatic conditions of the location of interest. For example, the table here shows some relevant climatic parameters for Ottawa with the appropriate values for the current climate normals and the predicted climate for the worst emission scenarios for 2050. The selection of a potential candidate can be done with any suitable weather database. The Appendix C of the NBC is a suitable source for this, which will be used for this example. The tables located within the ASHRAE Handbooks of Fundamentals are also suitable sources for this work. The tables show current weather data found in the Appendix C for downtown Ottawa. The climatic parameters that can be used here is mostly heating degree days, but we'll also use annual total precipitation for more precision in our selection. Additional information, such as cooling degree days, would be even better since the change is significant, but that information is not listed in the NBC. The idea then is to go through the table and identify suitable candidates. The following 4 cities have heating degree days and annual precipitation similar to the target values, with Port Burwell and St. Thomas being the closest. Other cities could have been selected, but for the sake of the demonstration, we'll be using these. Looking up those cities on the map, we see that they are all located southwest of Toronto. Basically, the future climate of Ottawa in 2050 could be similar to today's climate in southwestern Ontario. At this point, a designer could select the design data for one of these cities to represent the future climate for Ottawa. But this selection does not account for 2 important parameters. The solar availability or solar irradiation has not been validated, and we can expect that southwestern Ontario has more sunlight than Ottawa. How will that impact your design? Also, the selected locations shown here are nested between 2 of the Great Lakes, while Ottawa is a river city. How does that affect humidity loads and rain events in your design? So as you can see, the analog location approach can be helpful, but it has its limitations. Some tools exist on the internet to help select an analog location. Here, using the FitLab City app, a series of analog locations are considered and used to draw what they call a climate similarity map. The map suggests that cities located in Chicago or Detroit-Toledo regions could be suitable to represent Ottawa in 2080, so at the end of the century, rather than 2050 that we used for the previous example. Actually, when considering the information for 2080 based on the analog approach of the previous example, we tend to end up in the Detroit region. So both approach and the tools show similar results. As mentioned before, care must be exercised when doing the analog climate location approach, since the solar availability for the regions shown here are significantly different than for those of Ottawa. Moving on to weather files for energy modeling. But first, some background information on these files. Weather files for building energy modelings are often called typical meteorological year, TMY, since they represent the climate normal for an entire calendar year. There are various formats: the YEC used by ASHRAE, the CWEC used by Environment Canada, for example. All these files contain information relevant to the building energy modeling industry. For each of the 8,760 hours, we can find temperature, humidity, wind, solar irradiation, and more information sometimes. These files are created using real weather data. The process involves selecting the historical month more closely representing the climate normal for that month, using various weighting factors. Then all the selected months are assembled together, and some smoothing is done at the junctions between the months to have a full year that makes some logical sense. In this manner, the weather file most closely represents the climatic normal for the location on a month-per-month basis. The example here shows which months were selected to create the most recent CWET file for the month for Montreal. In order to use a TMY file to represent the future climate of a city of interest, the principle of analog location could be again used with the same limitations. However, over the years, two alternative options have been developed. The first one is to morph a TMY file into a new file representing the expected climate change. The second one is to create new TMY files using appropriately selected historical months that are deemed to represent the expected climate change. Morphing is a tricky process. It involves the application of mathematical transformation to the data within the file. This transformation is similar to geometrical translation and scaling operations. The shifting involves adding or subtracting a value from the original data. This value should be selected to represent the climate anomaly for that value. Stretching involves multiplication or division of the original data. This is used to represent a relative change due to climate change, often represented by a percentage change in the various reports. Both transformations can be applied to the same data along with some appropriate constraints. For example, a value could not be lower than 0 for absolute humidity, for example. Each variable in the TMY file is subjected to a given set of transformation, one or the other or both. The climate anomalies used are obtained for a given climate change scenario. There are some pros and cons to this approach. One of the main advantages is that it can be very fast, especially if you are using an appropriate software, which could be Excel-based, for example. A single file could be processed in a matter of minutes with appropriate software. However, depending on the software used, the user can run into some limitations regarding which climate scenario can be applied. Another advantage is that it starts with the TMY for the locations, so it is expected that the local climate patterns are maintained and, once modified, are still representative of the future. However, each transformation is applied individually to each variable. This could generate some loss of cohesion between them, resulting in a TMY file that is not so representative. For example, a rising temperature in the summer is often associated with an increase in air humidity content, but the applied transformation could ignore this trend. There are some software tools available on the web to help practitioners morph TMY files. They are listed here with some of their limitations. The second one is commercial, and to obtain the TMY file produced, you need to pay a small fee for that. In case you are looking to develop your own morphing tool, here is a suite of suitable references for consultation. If you ever do develop your own tool, I would be happy to take a look at it and confirm that it gives a good result. So the other approach is the creation of future meteorological year, which are using a process similar to the creation of TMY files, which means that we start with obtaining the climatic anomalies applicable for the scenario, the period, and the median that we are looking for. Then we go through the historical months to select representative ones that we then assemble together to create the FMY file. This approach has a benefit of being, again, location specific. It has no limitation on climatic scenario, and it uses real recorded weather, which means that without modification, which means that the climatic sequences that are in the file did occur, they are real, and that cohesion between the variable is ensured, so that raises the somewhat the confidence level in the result. It is, however, a lengthy process, especially if it's manual. The quality of the FMWire file created depends on the quality of the source data. If there is any missing information in the historical months, then we have a problem with our file. But again, even though the confidence can be higher with this approach, we can still question the fact that it may not be a real representation of the future climatic sequences. Regardless, instead of waiting for more official FMWire files from Environment Canada, SLCan had an external contract executed to create such files for our own use. We selected 15 major cities across Canada for a mid-range emission scenario for 2050. So basically, we were assuming that we would miss the 2°C target. The historical months selected are based on the monthly mean temperature change only to speed up the process, and various file formats were created for our use. Going quickly through the results of this contract, so first we identified the temperature change that needed to occur or that would occur for each month for each city, and then that helped us set a target that was then used to select the appropriate historical month to constitute our FMWire files. The table here shows to the left the month selected for the creation of the typical meteorological year, and to the right the month selected for the creation of the FMWire file. One thing of interest is that some of the historical months selected go as far back as the 60s. Overall, the result is very satisfactory, with a small average error between the selected months and the target. We ran into some issues with 1 month for Quebec City and 2 months for Vancouver due to not being able to find a historical month matching our target. So we had to select the closest month and make some adjustment to the values within in order to reduce the error. Overall, we feel that the result is very satisfactory. On the left, you have the temperature change and the 18 degree change between the normal and the climate change targets we selected. On the right, you have the solar irradiation profiles for each cases. That's interesting to note that even though the temperature change was closely matched for Ottawa, the solar irradiations is significantly different between the normal and the new file. This is not unexpected in the sense that we did not select the month based on solar irradiation. And it also serves to show that the increase in temperature that we expect to see across the world is not necessarily tied with an increase in solar irradiation on the ground. Actually, going through the literature to find some background information on this, the literature seems to suggest so far that the world will actually see a reduction in solar irradiation at the ground level due to an increase in aerosol concentration in the atmosphere. But this is the confidence level of this statement is not very high. So basically, so far the interpretation that we make of this information is that is better defined by status quo regarding solar irradiation. So this work means that we have one weather file showing one possible future meteorological year. We are going to use that in our internal works to better evaluate the impact of climate change on some of our buildings. The question remains about if we need more files for more climate scenarios. Future will say. So in summary, using weather information based on climate normals is may no longer be adequate because of the pace at which the climate is changing. The source of climate change data is informative, but its use for designing building can be limited. There are some works underway to fill that gap for the building industry. So pay attention to what is out there, and you should be able to find information to help you in your work. Thank you all for your attention, and we're now ready to take some questions.
Thanks, Frederick. We do have one comment from the attendees. One is that the future weather files have been developed for British Columbia, and I think that you mentioned that on your second from last slide, that there are some weather files that have been developed in different jurisdictions. This one indicates that the future weather files for BC are available at www.pacificclimate.org under their data files.
Just let me go back to. Okay, no, it's not. Okay, that's good to know. I could add that to my list of resources here.
Right. One question that I had was about how do you validate the towards the end of your presentation, you were talking about the validation of the FMY there. Can you explain a little bit further about how you can validate the model in terms of accuracy? How is it, because it's a forecast, how do you validate? That's a question I had.
Well, it's more to look at the quality of the file, the file that we have. Right. Does it make sense what we see there? Is it, of course, we cannot compare with the future, but is there any aberration that we see when looking at it? Is it, if we expect to see more cooling degree days, do we observe more cooling degree days as a result? So in that sense, we do some validation. I see. So that's how we notice the solar irradiation profile being quite different, and interestingly so, that triggered some additional questions.
And you mentioned that there's a moderate amount of smoothing using the FMY process. Is that just at within the first few days of the month and the last few days of the previous month? You were mentioning that it was smoothing. How is that smoothing done?
Yeah, actually, the TMY process talks about smoothing over over 12 hours at the junction. So 6 hours before and 6 hours after.
I see. So it's very nominal, like a very small amount of smoothing on the tail end and the beginning end of each month.
Yeah, to avoid a big jump of 20 degrees C, for example, between months, between hours.
Between hours, right. Right. No, that's very helpful. No, I think that this is fantastic information. I think that's the end of our questions at this point, Frederick, but thank you very much for making this presentation to us. And if you could just pop your email address up on the screen again, if there's any additional questions from the attendees, we can have them reach out to you directly by email. I appreciate that. We are at the top of the hour, so I just want to extend my thanks again for you making this presentation to us today. Thank you very much. It was great.
Thanks for the opportunity.
Okay. Thanks, everyone. See you again next month. Bye for now.